A few years after special relativity, Einstein published general relativity, and in there he describes gravity in terms of space-time curvature. And space-time curvature comes from our observations of what we measure with rulers and clocks. No matter what you use for a ruler or a clock, the measurements vary from place to place in the universe in a gravitational field. So we interpret those measurements as space-time curvature. And so general relativity is a geometric model of gravity. It's all based on geometry, and it's led to volumes of textbooks on the mathematics and geometry and differential geometry and all kinds of advancements in physics and science because of it. And general relativity is a very well-tested theory. There's been all kinds of experiments, such as measuring the perihelion of Mercury and the decay of binary star systems, things like that. The polarizable vacuum model is essentially an alternate interpretation of gravity. It's still, in a sense, geometrical in that it's what we measure with rulers and clocks. But rather than refer to space-time as being curved, we refer to the rulers and clocks vary from place to place because they're immersed in a polarizable vacuum medium. And as the polarizability changes, rulers and clocks change. As the energy density of the polarizable vacuum increases, rulers shrink, clocks run slower. And so it's a different interpretation of the same observations. Up till recently, there were differences between the polarizable vacuum and general relativity. In a weak field, they both predict the same results, but in a strong field, they differ. However, recent developments, publication by Dr. Joe Depp, show that you can derive exact solutions that match general relativity from the polarizable vacuum model with a small variation in the Lagrangian density that was originally published by Dickey in, I think, 1957. Now it puts the polarizable vacuum on the same footing as general relativity. If you derive the Schwarzschild solution for a spherical mass distribution from both models identical, you get identical results. So in that sense, the polarizable vacuum is just an alternate interpretation of the same measurements that are interpreted as space-time curvature under general relativity. What we've done here at Delta Group Engineering is take the polarizable vacuum model and describe it in terms of a medium that's built upon a frequency distribution. We take the wave functions of virtual particles, photons, fields, and describe the polarizable vacuum in terms of waves, so that the polarizability is described in terms of a Fourier transform, and so that we can model gravity based on wave functions and the propagation of waves through the polarizable vacuum. And it gives us an advantage in that it allows us to take a step forward and look at gravity in a way that can be used for engineering purposes. Throughout the past 100 years, there has been no real engineering from general relativity, simply because engineers are at a loss on how to modify the curvature of empty space without dealing with large planets and black holes and things. General relativity, the space-time curvature depends on the energy density of the local environment. The Earth has a certain energy density, and the gravitational field around it depends on that. In EGM, which stands for Electro-Gravi-Magnetics, we take and use a Fourier distribution of frequencies to describe the gravitational field through the polarizable vacuum. It's the Fourier distribution is a superposition of fields. It's many frequencies, many waves, different amplitudes, all summed together to describe what the vacuum is. And in that sense, energy density plays an essential role in determining our calculations. We've, in a sense, unified electromagnetism and gravity in terms of energy density, where it really doesn't matter what the theory is. EGM is a method that we use. It's a method of taking the energy density and making calculations that can make predictions. We can predict the value of G based on energy density of the environment. We can make predictions why it affects certain particles at their mass value and not some other value, like why gravitational mass and inertial mass are the same. All these things come about because we can now make calculations based on frequency modes, cutoff frequencies, the fundamental frequency, and the polarizable vacuum is harmonic in that we've got a fundamental, very low frequency fundamental, and that steps up through harmonics where the amplitude of those harmonics is going down, but the frequency is going up until we reach a cutoff. The cutoff frequency is a very high frequency, but it's not infinite. It's much, much higher than visible light. It's such that it would pass right through most metals, well, any metal at this sense, and that's why we can't shield gravity, because the frequencies at the cutoff, at the highest end of that spectrum, will pass right through to at those frequencies, molecules and crystals look like a lot of empty space. Interference. We use our application of EGM is to generate interference patterns in the vacuum. Using electromagnetic fields, we can concentrate energy in one area and void of it in another by generating an interference pattern. If we can detect what's locally there, we can interfere with that. And part of the model is that while we don't know exactly what's there, based on energy density at the surface of the Earth, for example, we can make an estimate of what's there. And then we know, in a sense, what needs to be added there to interfere with it. And in that sense, we may be able to modify gravity or mimic it, which is a little different than actually generating artificial gravity, but generating an electromagnetic effect that has the same apparent effects as gravity, such as levitation or artificial gravity that work by electromagnetism rather than large amounts of energy and matter as you would need in general relativity. Einstein's equivalence principle is very similar to what we're doing with EGM. The equivalence principle basically says that any experiment you do in a gravitational field could also be done in an accelerated reference frame, like a rocket lifting up at 1g of acceleration. And so they would be indistinguishable between a gravitational field and an accelerated reference frame. However, in reality, because planets are spherical and there's tidal forces that act horizontally, that are not, you would not find in an accelerated reference frame. So in that sense, it's not exact, but it's similar, and that similarity has been exploited throughout general relativity to put gravity in the same terms of an accelerated reference frame. In EGM, we take that method of similarity further. We use electromagnetic fields that we apply into interference patterns that generate accelerated reference frames. When we have an acceleration, that acceleration is equivalent to gravity, just because of the equivalence principle in the same sense. So what we engineer with EGM is, by similarity, equivalent to a gravitational field. Well, EGM, as I said, it's an extension of the polarizable vacuum model to something beyond just assuming that the vacuum is a polarizable medium. We actually take it one step further and describe that medium in terms of frequencies and modes and density of modes. So it allows us a tool that we can use to do engineering with, whereas empty space does not. Well, electro-gravi-magnetics, EGM, is not a theory. It's a method of doing calculations. We don't model a physical model. We don't try to say what a charge is or what an electron is or any of that stuff. We're not trying to compete with the standard model of particle physics or QED or any of that. We're using it as a method of calculation that's simply based on energy densities that are common throughout all of physics. You've got energy and it's got a volume, and we use this to calculate what modes could exist in that volume at this energy, at this energy density. We have a method of doing calculations. With it, we've not only been able to calculate G and model it as a Fourier series, we've also been able to calculate the radius of an electron, the radius of a proton, the radius of a neutron, because these radii depend on the energy density of the vacuum surrounding it. In general relativity, where space-time is curved, objects essentially change size. They contract. There's length contraction, time dilation in the gravitational field. Where gravity is stronger, objects get more compact. In EGM, this is a result from the energy density. As the energy density is greater, it's like a pressure that holds it together. So by knowing the energy density and calculating the energy density in that volume of space-time, based on our Fourier spectrum and a cutoff, we can calculate what the cutoff will be in order to give us a particular radius. And so we can model the radius of a proton or a neutron or an electron or anything, and our results are spot on accurate because it's all dependent on the energy density that holds it all together. That this radius is an equilibrium point between the energy density stored in that particle and the surrounding vacuum. In a sense, the equilibrium is kind of like thermal equilibrium. If a particle exists in a heat bath, for example, it will interact with photons, like an electron will interact with the photons, and it'll move around, but it'll establish a finite range of where it's located. Its location is X, but it's got a variation around that, a probability distribution of where you might find it. And that distribution depends on its interaction with the environment. And in that sense, the energy density of the vacuum at a particular location is going to determine the size of that probability distribution. We started out modeling just gravity at the surface of the Earth in this respect. And without any intention of coming up with a particle model, we've applied the same principles, the same cutoff calculations to particle physics and got accurate results, which was a surprise if nothing else. But it was not our goal, but it came out that way and it worked. Each particle is in a sense in equilibrium with the vacuum around it. And as a whole, that puts the planet at equilibrium with its environment. But we model, for example, we take the energy density of the Earth as a calculation based on its mass and its size. And then we say by similarity, the vacuum surrounding the Earth must have an equivalent energy density. So on top of what would be termed the electromagnetic zero-point field, we superimpose upon that the energy density of the Earth as a field, so we've got like the zero-point field plus the field of the Earth that are superimposed upon one another to give us a gravitational field, to give us a gradient in the energy density with respect to altitude. And it's that gradient in the energy density that we see as 1g of acceleration. Well, Haitian Rueda, for example, they're modeling the inertia of a particle as electromagnetic drag force. As you try to accelerate a particle in the vacuum, it interacts with the zero-point field, and that causes a drag force on the particle. Our model is very similar to that, but we've taken it to describe it in terms of the inductance and capacitance of the path. We have a charged particle in an electromagnetic zero-point field, and as you try to accelerate that particle along the path, it necessarily induces a magnetic field around it. That magnetic field generates what's called a gauge potential, a potential energy that's pushing the other way. And so when you try to accelerate the particle, a charged particle, it generates a magnetic field that then generates an electric field that opposes it. And this was also in Haitian Rueda's work, is the same kind of principle. And what's different is, rather than determine an arbitrary function of the environment and the frequencies, we take our Fourier distribution of the zero-point field and use that, so that we can describe what the inductance is on a path depending on the energy density. And we can describe that the amount of inertia depends inversely on the wavelength, for example, and mass is inversely proportional to the wavelength of the wave function. And it's actually, what we measure is the contraction of that wavelength when you attempt to accelerate it. They talk about, Haitian Rueda talk about an event horizon at the particle level, that when you attempt to accelerate it, it causes an event horizon, a place where the velocity would have to exceed the speed of light. And in a sense, it's the same thing. When the electron, for example, charged particle in a zero-point field, is jittering around, jumping around, because it's interacting with the photons in the field in an equilibrium, like a handshake. I give you a photon, you give me a photon, and I move this way, you move that way, and we keep, and it dances, in a sense, with the vacuum. What happens when you try to accelerate it is that the electron's motion is already occurring at the speed of light. It can't go any faster than that. So when you try to accelerate, all you're doing is contracting that probability distribution. And that contraction requires an input of energy, and it's that input of energy that we measure as inertia, that you have to add energy to accelerate the mass of an electron. The Haranoff-Baum effect is essentially, if you have a magnetic flux passing through, say in this direction, we have a magnetic flux. Circulating around this magnetic flux is the gauge potential A, the magnetic vector potential. And essentially what the Haranoff-Baum effect is when you have an electron wave function passing on either side of that flux line, you get a phase shift depending on which direction it's going with respect to the gauge potential. So if it passes to the right, say, it gains phase. If it passes to the left, it loses phase. And what essentially gravity comes down to for a charged particle at inertia is the interaction of the charged particle with the magnetic flux in the vacuum. The magnetic gauge potential is nothing more than flux lines in the vacuum, and each flux line that interacts with the charged particle adds 2 pi to the wave function, 2 pi phase to the wave function. So in a sense, magnetic flux in the vacuum acts like resistance in a superconductor. In a superconductor, you can have the Haranoff-Baum effect measured there as well, and you get a phase shift in the wave function of the electrons in the superconductor. When electrons travel through a superconductor, it should be completely resistanceless. It should have 0 resistance. But when you have magnetic flux lines passing through it, or trapped vortices as they call it, every time the wave function passes a vortex, it gains 2 pi phase. So it is a resistance. It slows down the speed of the electron. Well, a free particle passing through a polarizable vacuum also interacts with magnetic flux in the vacuum. And in a sense, it's this magnetic flux that it interacts with that determines the speed of light, that determines the polarizability, determines it's part of the energy density, the density of flux lines. So if we want to modify gravity or modify the speed of light, we need to have control over the flux that is interacting with the charged particles passing through it. For example, if an electron is propagating in this direction and there's a magnetic flux line, it crosses that path, then it'll circulate 2 pi around it. Well, that slowed it down. That's what I mean by it gains or loses phase. The actual experiments that have been done for the Aharonov-Bohm effect basically take 2 electron beams, they split the beam, they pass one beam to the left of the flux line and one beam to the right of the flux line, and then the 2 beams interact on a photographic film to produce light and dark interference patterns. And the interference pattern on the film depends on the phase shift that each path had added or subtracted from that electron beam. So we can photograph and determine how much phase shift you get from how much magnetic flux. In a gravitational field, under our model anyway, we have magnetic flux is the primary constituent of the vacuum, so to speak. The polarizable vacuum, to us, where we model it as an electromagnetic field and inertia as electromagnetic drag, we have a density variation in the flux lines. And it's this density variation that causes variations in the refractive index and the coefficient of reflection. And that's where an electron, say, falling in a gravitational field, is falling because it's interacting with flux lines that want to make it phase shift and therefore move in that direction. The Aharonov-Bohm effect, when you look at it quantum mechanically and then extend that to a macroscopic analogy, it really turns out to be that the Aharonov-Bohm effect is responsible for the Lorentz force. The Lorentz force is what we use to turn electric motors, generators, all these things. On a macroscopic scale, we see it as QE times V cross B, which is the charge times the electric field times the velocity of the charge in the magnetic field. But on a quantum scale, it's really the Aharonov-Bohm effect inducing a phase shift in each charged particle's wave function. In our model and in a recent paper by J. Johansen in, I think it's Norway, I check on there. He published a paper that showed that gravity can result from the depolarization of the vacuum due to the interaction between 2 charged particles. If you have, for example, an electron at point A that jittering around, broadcasting its frequency spectrum, it interacts with another electron that's also jittering around, broadcasting its frequency spectrum. And although the 2 charged particles are both negative and the electric fields want to repel, there's still a slight amount of gravity between them that the electric field overwhelms, but it's still there. And the way that's explained is that the electromagnetic waves from one interfering with the other cause it to move within within that field by Lorentz forces. For example, if you have an electron at this point and I have an electromagnetic wave coming at that point, we have the electric field will drive the electron up and down in the direction of the electric field. It's being driven up and down in a magnetic field which is perpendicular to the electric field. And because of the Lorentz force, V cross B, it exerts a force on the charged particle to move forward. So the electromagnetic wave moving in this direction exerts a force on the electron in that direction. However, if the frequency of the electromagnetic wave is equal to the natural resonant frequency of the electron in the polarizable vacuum, something strange happens. The phase inverts. So you get a 180-degree reversal in the phase. So instead of the electric field driving the electron with the field, it drives it against the field in the opposite direction, so that as it interacts with the magnetic field, it moves toward it. So it reverses the phase, and it reverses the direction that the electromagnetic wave has on that particle. So in a sense, we can describe gravity as the Lorentz force taking place at that scale of the individual charges in the vacuum. We start with the foundation that even electromagnetic fields in free space have gravity, and we understand electromagnetic fields very well. So if an electromagnetic field has gravity, then everything about gravity should be explainable from what we know about electromagnetic fields. So we use this as a starting point, and this is where we started out in developing EGM, is that gravity can be modeled in terms of electromagnetism. We use similarity by deriving the equations using Buckingham's pi theory, and we've also done physics by research, Johansson's paper, Depp's paper, all these different sources to come up with the methods of calculation that we use. But we don't actually claim to have grand unified electricity and magnetism, other than we unified it in terms of energy density, which is common to both things. In using EGM, we've made a number of calculations and come to some various conclusions of what might be possible. So far, we haven't had any verifiable experiments other than what's been done in terms of particle physics to confirm the standard model. The calculations, for example, of our particle radii match those by the particle data group. And so we know that as far as experimental evidence is concerned, what's already out there fits EGM. But what EGM is intended to do, it's intended to give engineers a tool by which they can understand and modify gravity. It could lead to things like artificial gravity, electric motors that can defy gravity. It could lead to modification of the speed of light, warp drive, things like that. Electromagnetic propulsion. Being able to generate gravitational fields artificially could also lead to gravitational astronomy, because if you can generate a gravitational field with an electromagnetic device, then gravitational waves can also generate an electromagnetic signal that we can monitor. And so in that regard, EGM is a tool that can be used to help facilitate these things and make them happen. Well, some of the technologies that we have on the drawing board right now are like an electric motor that does not require a housing. It's like an armature that turns itself. We've also got on the drawing board some ideas for electric motors that could defy gravity. However, the problem with all of these devices is none of them are small. The amount of energy required is large. It's the cost to develop the actual devices themselves is not small. And so we haven't made much progress in terms of actually building one. But we're hoping that in the near future we will. We're already started investigating ways of getting these things tested and built. In 1994, Miguel Alcubierre wrote a paper that was published in Classical and Quantum Gravity, the journal, where he proposed a solution of Einstein's equations for general relativity that allow one region of space-time to move faster than light relative to another region of space-time. And anything carried along in that space-time does not experience time dilation, length contraction, which, if you're familiar with special relativity, these things are inherent. Whenever you try to accelerate an object to the speed of light, length contracts, time slows down, energy approaches infinity. So you can never exceed that speed of light barrier. But with Alcubierre's equation, they call it the Alcubierre work metric, with this equation, it shows that you can take one region of space-time and move it faster than light relative to another, and anything in that region of space-time is carried along with it faster than light, with no time dilation, no length contraction, and reasonable amounts of energy. However, one thing that came out of that equation is that it requires something they call exotic matter. Exotic matter is negative energy density. And from what we know of general relativity and vector calculus and tensor analysis, this is something non-physical. All energy has a positive energy density. So there have been a lot of papers published in the last 10 years about this, about the exotic matter requirements. It's gone from requiring more exotic matter than could be found in the galaxy to slightly more than what you would need in quantum uncertainty. So what I mean by that is that there's an uncertainty in what energy density is there. So over very short periods of time and very short distances, energy density could be negative. We can't measure it. It's an uncertainty in that measurement. But the requirements for exotic matter have dropped substantially, but it's still required. Recent papers have shown that using Alcubierre's warp drive metric, you would need exotic matter even if you didn't travel faster than light. It's inherent in that particular equation. It's also there in wormholes, transversal wormholes. Any place you would use to try to make a shortcut through space-time would require exotic matter. What we've come up with is something slightly different. It's similar, again, based on a similarity, that we've taken the Lagrangian density for an electromagnetic field interacting with charged matter, and we square that. And what we get, term for term, is an electromagnetic version of Alcubierre's metric. It's not exactly the same, obviously. Alcubierre's metric is referring to a space-time, where ours is referring to an electromagnetic field. But term for term, it's the same. What it shows is that using reactive power, and by reactive power is something common, it's not uncommon, it's used to describe the power flow in transformers, like transmission lines of power to homes, everywhere else. For example, in a capacitor, the voltage on the capacitor and the current into the capacitor are 90 degrees out of phase. This is described by an imaginary number. Imaginary numbers are used all throughout physics to describe wave properties. Waves are vectors rotating in what we call the complex plane, which is a real axis and an imaginary axis. And what we've shown is that if you use reactive power in our electromagnetic metric, we get an imaginary field that when you take the square of that field, we end up with a negative potential energy density. It's physical, it's not non-physical, but in a sense where in Alcubierre's equation, you have to essentially, to get negative energy density, you have to extract energy from the vacuum. And the way warp drive in that works is that you're extracting energy from the vacuum behind you, so space-time expands, and then moving it in front of you, so space-time contracts, and in doing so you move the center of mass forward, and that carries everything forward. What our electromagnetic metric shows is that we store potential energy in the device using reactive power, reactive energy. It's energy that circulates from inductor to capacitor, from current to voltage. It circulates out of phase, 90 degrees out of phase, like and so it generates an imaginary number, but it's real energy. When you take and calculate the energy density, just like you do with Alcubierre's metric, we get a positive number because we start with an imaginary quantity that's physically real, potential energy stored in the device. We then compare this and find that what we get is that to do work, to move the center of mass forward, we redistribute that potential energy in the field. Instead of extracting energy from the vacuum, we take the energy that's in the field that's symmetrical and move energy from this side to that side to make it the same effect as the Alcubierre warp drive, in that we shift the center of mass forward by extracting energy from our potential, from our circuit. And what it means in terms of electronics is simply that we're phase shifting away from that 90 degrees out of phase, more in phase, which allows us to do work with the field. And it's the work that we do, that phase shift, that allows us to move it forward. And that phase shift is the same phase shift in the quantum wave function we talk about, the Aharonov-Bohm effect. Here, we're using it on a macroscopic scale as a Lorentz force to move the device forward and carry its mass forward. But it doesn't require extracting energy from the vacuum, it doesn't require negative energy density. So in this sense, it's not only physical, it's practical. In Alcubierre's warp drive metric, it's not really a wave, it's really a space-time that's moving. The walls of this space-time are what require the exotic matter, and it's through the walls that you run into problems, because the walls exist in empty space, out somewhere around you, and that inside this work bubble is all the matter that you're moving forward. But it's something has to generate in empty space, this work bubble. It's unphysical and we don't know how to do it. But with our electromagnetic metric, it's physical. So really what it is we're generating an electromagnetic wave and then interacting with it in the right phase to generate an asymmetrical force that wants to move it in one direction and carry the center of mass forward. In a sense, it is like riding a wave, because we're generating this wave and then we're carrying ourselves along with it, just like a surfer. Breaking the light speed barrier, since the release of special relativity 100 years ago, has been something that can't be done. People, immediately, you can't go faster than the speed of light. It would require an infinite amount of energy. But that infinite amount of energy is totally dependent on what you put into it, and you can't get more than what you put in. And it depends on the time dilation and length contraction. That same factor is what causes the energy to blow up, and you can't get there. You can't get to the speed of light. What EGM allows us to do is describe the refractive index of the vacuum as a variable. So it describes the speed of light as a variable that depends on energy density. Essentially, to raise the speed of light, we would have to lower the energy density. Obviously, this sounds difficult because you would need to extract energy from the vacuum. It's not something that is readily apparent that we can do this. What we propose with our electromagnetic metric is a little different in that we assume in our model that the drag force of inertia is caused by a Lorentz force acting on charged particles. So we've derived that our electromagnetic metric, if everything traveling along with it was charged, oscillating at the same frequency as the waves in the device, that all the charged matter would be carried along with it by the Lorentz force. And there would be no time dilation. The energy in the device remains a constant of the motion. So in that sense, it could be able to travel up to and beyond the speed of light because the energy is not going to infinity. But in order to do this, it's sort of like saying that we're going to control the motion of every charged particle moving along with it. It's obviously not an easy task. But what we've considered, and this is just conjecture at this point, is that like a high voltage electric power line worker, he wants to be safe. So when he goes up to work on the power lines, he connects himself to that power line. So he's at the same potential as that line. And that line could be 10,000 volts or more. It's 60 hertz or 50 hertz oscillating current flowing through it. There's charge flowing through it, and he's at that potential. And so as that oscillating wave of charge flows through the wire, it flows through his body, his cart, everything, so that he's far away from the opposite potential, even though that potential is oscillating at 60 hertz. So he's safe that way. But that, in a sense, every charged particle in his body and in that cart that's holding him is oscillating along with the current flowing through the wire. Electrical power line workers, routinely they attach themselves to the wire they're working on, even if that wire is at 10,000 volts potential oscillating at 60 hertz or 50 hertz. And he does this for safety. He attaches himself, the cart he's in, and everything to that wire so that everything nearby him is at the same potential. And in doing so, he's safe as long as he doesn't get in contact with the ground or the opposite potential. And so our hypothesis is that with our electromagnetic metric, if we can couple all the cargo and crew to the charged hull of the device, in a sense, they will carry the same charge and current that is passing through the hull at the same frequency, so that all the matter being transported is oscillating with electrical current at the same potential. And so the field that's moving the device forward will also carry everything with it. And the carrying with it, you wouldn't feel any acceleration, you would feel inertia, just normal inertial reference frame, no acceleration, you're just traveling along. So the device should carry everything forward just like we would like it to happen in a warp drive. But this is talking about a physical model and a practical application. We've coined the phrase semi-exotic matter for any kind of matter that's carrying the electrical current that matches the field. And when any kind of matter carries the right electrical current at the right phase in that field, it will be carried along with it. So this is our hypothesis on actually designing something that would be equivalent to a warp drive. Regarding extracting energy from the vacuum, I know it's been proposed by Al Puthoff because of the polarizable vacuum model and the idea of a zero-point electromagnetic field, that if we could extract energy from the vacuum, it would essentially raise the speed of light and reduce the refractive index. So these would all be excellent things to have if we could do it. Right now, it hasn't been done, and we're not exactly sure how you would do it. But one possibility has been to try to interfere with the waves in the vacuum. And what we mean by this is based on our EGM model. With EGM, we model the vacuum as the Fourier series of wave functions and different harmonics and waves. And if we can destructively interfere with those waves by applying another field on top of it, it's possible to reduce the energy density in that volume of space-time and lower the refractive index, and in a sense cancel the energy that's there, but really that's not the same as extracting it. We're not extracting that energy to do work, but we're eliminating what's there, and that by applying more energy. And that's where we think it would lead to, is that it could be possible to reduce the refractive index and raise the speed of light without actually having to extract energy from the vacuum, just cancel what's there by applying another field that interferes with it destructively out of phase.